everyone. My name is Alice. I'm education lead at ZKM. This is the first part of generating zkMIPS proofs with ZKM. So we'll be going over an overview of zkMIPS, its different components, and then also a demo of generating and verifying a proof using ZKM's new project template. It's a very convenient template to use if you're a dev and want to create an end-to-end project using zkMIPS. We previously did release a similar video demo, but this is the version that incorporates some new updates based on our new release, including that new project template. So in our first part with zkMIPS, we'll be breaking down step by step the question, what exactly is ZKM? ZKM is a general purpose zkVM for verifiable computation that's based on the MIPS architecture. Our zkVM is called zkMIPS. But what does this actually mean? Let's break down this even further. So we'll first start off with verifiable computation. Now, today, if we want to ensure that any type of computation was correctly done, we would have to verify the accuracy and integrity of the result of that computation. We currently have two different ways of doing this. So one through an outsourced trust method and another through self-verification. So the first one, outsourcing the trust, relies on trusting some sort of external entity or third party to perform the computation correctly and provide that correct result. So you're basically delegating that computation task to someone else, like, for example, a cloud service provider, which is typically a centralized service or database like AWS, and trusting that they're doing it correctly and not tampering or changing the results. So there's a very huge trust assumption that's involved here in this first method. The other method, if you're not really comfortable with the first one, is doing the computation yourself through self-verification. So that involves rerunning the computation on your own end. And this method gets rid of that trust assumption, but it's very costly and it's also inefficient because it's repetitive. It's also duplicative to run a computation that has already been run before. So it's not very efficient. And as you can see, each of our two models here have different trade-offs in terms of costs, security, scalability, transparency, while our first model here for outsourcing that computation relies on trust and may lack in security and transparency. It's also more scalable and cheaper than re-executing that computation, which is involved in the second method. So there's trade-offs within each. But what if there was a way to get the best of both worlds here? Is there a way where we can make it cheap and scalable for a third party to verify a computation without having to rely on trust? That's where the idea of a proof of knowledge and ZK comes in. So we may be able to find a solution through verifiable computation. So with proofs of knowledge, it's a two-party protocol that involves a prover. That can be like a single user, a client like yourself, who can outsource the computation to a verifier. And that's typically a more computationally powerful party, like, for example, some servers in the cloud, who is able to verify the correctness of that result. A proof of knowledge describes that dynamic between that prover and the verifier. So the prover, like what we said, is typically more computationally powerful. The verifier is less so, could be the user, like yourself. And that prover will convince the verifier that it knows the valid solution to some instance of a computational problem. That prover will perform that computation and then produce the result of the execution, as well as a proof that that computation was correctly done. And then both that execution result and that proof will get sent to the other party, who is the verifier, and they'll basically check that the proof to verify that the computation was indeed executed correctly. Looking at this interaction in this diagram here, the verifier will say, well, I have an entry X and a function F. X is an input to F, and the verifier will ask the prover to compute the result Y. And the prover here will compute that result Y. And in addition to this proof, in addition to this, we'll also produce a proof W that's then sent to the verifier. And that verifier will check if that proof is valid. So this diagram here was taken from a course that we offer on our Education Hub called A High-Level Intro to ZK and Snarks. If you want to learn some more about verifiable computation, I highly recommend you check out this lecture, which I have linked right here. And continuing this, when we say computational problems, what exactly do we mean from this? So some examples include, for example, the problem of factoring, finding the time factorization of a given number, which is a pretty common toy example used in a lot of zkVMs. Another example is finding the discrete log of an expression, which ties into the discrete log problem. Another could be, I know the private key that corresponds to a public key. That's also ties into the challenge response protocol in public key cryptography. And that's how your browser authenticates a site certificate. So in that example, in authenticating a site certificate with your browser, it involves both a public and private key pair. So data that has been encrypted with a public key can only be decrypted with its corresponding private key. And then another example is for a computational problem, the validity of a signature from an ECDSA, which uses keys from elliptic curve cryptography, and that ties a lot into signature verification. In convincing the verifier that a computation was done correctly, there's a couple of questions that you may think of. One is, why can't we just rerun the program and produce a dump of the entire execution of that program? Or better yet, why don't we just reveal the solution of that computational problem instead of doing, all of this work of producing an execution result, producing a proof, and then sending both of these to the verifier to check? Why do we need to do all this work? There's a couple of reasons why this is not a great idea. For one, that resulting proof would be way too long to verify. And the verifier would have to replicate the entire computation that's done by the prover. That's really counterintuitive because we're essentially doing double work here. And the verifier also may not have the computational resources to do this. In zkMIPS specifically, the sequence of states by rerunning the program would be way too large for the smart contract, which it acts as our verifier to verify. So this is not exactly possible. The point of having verifiable computation is that all of that difficult, long work is able to be outsourced to that computationally more powerful prover, while the verifier's work is as simple as possible. So ideally, because of this, we want our proof to be short and easy to verify, or in other words, succinct. And another reason is that maybe the prover wants to keep the solution a secret. This privacy component is also known as zero knowledge. And for ZK-specific proofs, that proof will not reveal any additional information about that solution. So that information is kept private. I'd also like to emphasize that a lot of projects nowadays use ZK to mean privacy when they really mean succinctness. So it's really good to have that distinguishing there. ZKM is specifically focused on that succinctness aspect of the proof, not the privacy aspect. And when we're applying proofs of knowledge to blockchain applications, there's a few properties that we need to consider for the proofs. So one is non-interactiveness between the prover and verifier. This makes it so that the parties involved can be untrusted, and it also allows for a larger number of observers to verify the proof, not just a single entity. Another is succinctness, which we saw previously means short, and the ZK property is optional here. The types of computational problems that these proofs of knowledge can be applied to, for example, are transition functions for L2s. We see this a lot in ZK rollups. So essentially, the layer 1 is the verifier, while the layer 2 is the prover. The layer 1, for example, it could be Ethereum. It's like a computer in the cloud, so there's some challenges where it could be slow, could be expensive. Scalability of the computations is an issue. So the idea here for these ZK rollups is to outsource those computations off-chain from the layer 1 onto the layer 2, and then the layer 2 would send the resulting new state with a proof back to the layer 1. So you're offloading computation. Another example is the execution of smart contracts. That's the main function for zkEVMs. Those are typically written in Solidity. The EVM will verify the execution of that contract. And a third example is the execution of off-chain programs as seen in zkVMs, like what we do at zkMIPS. So in zkM's case, an off-chain MIPS program is given, and zkMIPS will verify the execution of that program on-chain. The computational problem within ZKM is to verify the correctness of the execution of a program. And the solution comes in the form of an execution trace. And that execution trace you can think of as a complete record of the computation that's executed from running that program. And it's pretty commonly represented in a table form. So the columns are represented as CPU variables. The rows are the individual steps of the computation. And the verification process of that execution trace involves checking that each row of the trace matches the respective instruction of the program. And some examples of programs to verify on zkMIPS, for example, are the correctness of blockchain transactions, maybe some smart contract function calls, transactions on rollups. Those are just a few different programs that can be verified. Now that we've covered verifiable computation, let's go on to the next part, zkVM. To understand what a zkVM is, we first need to answer what a VM or a virtual machine is. You can think of a VM as a kind of program that can run other programs. So for example, EVM is a type of VM that can run Ethereum smart contracts. But in a VM, what we have here is a program that is compiled down to VM readable code or machine code, as well as an input to that program. Both that input and program are fed into the VM, and then a final state for that program is outputted. A zkVM adds onto the VM with a few extra components. So for a zkVM, you can think of it as a ZK circuit that runs a VM in order to prove that a program was correctly executed. In addition to this input and the program that's compiled to machine code, and just a note, the format for that is largely dictated by the choice of the ISA or instruction set architecture. So in this case, for ZKM, we're using MIPS. So it's compiled down to MIPS. But there's also, in addition to both our compiled down program and our input, there's also the witness. The witness are the values that the verifier doesn't read, either because they're private to the prover, so they kind of act as secret inputs, or because they're just too long for the proof to be succinct, so they just aren't included. The input, the program, and the witness are then fed into the zkVM, where in addition to the output of that program, there is also a proof for the correct execution of the program that's generated as a result. In the bigger picture, if we look at the placement of the zkVM with all the other components that are involved, including our compiler and the VM, we can first see here that that program will be fed into the compiler. So in zkMIPS's case, that compiler will compile the program to MIPS. That compiled program and any kinds of user-specified inputs, both public and private, are fed into the VM to generate a trace record. So remember that trace record is a complete record of the computation that's executed from running the program. And that trace record is then fed into the zkVM, which contains the prover. And then we'll look into some more specific components of the prover later down the line, but that will output the final proof that we see here. Now, why zkVMs? Now that we know what zero-knowledge proofs are and zkVMs, we'll go into the why behind zkVM specifically. So why should we use one in the first place? If we take a closer look at the stages of the life cycle for ZK proofs, we can see it first starts with the end user's action. So the end user wants to prove the correct execution of a computation. That's really the business logic part for applications. So the main question that you want to answer here is what exactly do I want to prove? So some examples like what we previously talked about, like smart contract function calls, maybe some token transfers on a rollup. You want to prove the execution of some transaction. It could be a variety of different things. From there, we need to determine how will this be executed. So if the computation is in the form of a program, that program will be executed in an environment that's able to compile to a readable format, such as an algebraic circuit or a machine code. For ZKM, that program is compiled to MIPS. And then our next step is how will our proof be generated so that we can have a proof for that program's correct execution. There are a few different ways you could generate that proof locally, or you can outsource it to use a proving surface or a proving market. The means of it doesn't really matter too much, just up to your preference and depending on the hardware requirements that you have. And now that we have our proof, we need it to be verified. So this can be done off-chain or on-chain. So for on-chain cases, we could use verification layers or directly on Ethereum by posting it on a smart contract. And with the proof, if integrated, a resulting action will occur depending on the application that it's being used for. For example, settling a transaction. And from there, that cycle repeats. Now, the vision here is, what if a proof of execution can be provided for any type of computation? So here we can think of both those that are based on the blockchain and also non-blockchain based ones. Now, this is the main vision that zkVMs are attempting to fulfill, where a proof can be provided to any sort of general computation, both those within blockchain and also those that are applied to non-blockchain use cases. So zkVMs like ZKM are able to address each stage of this proof lifecycle. And its main value proposition is a developer-friendly experience. So developers can write programs to prove using high-level languages that they're already familiar with, instead of using ZK DSLs or writing the circuit directly, which are both difficult, have a significant learning curve attached. So the main value proposition here is just contributing to the overall developer experience. And zkVMs here provide an execution environment in the form of a VM to execute the program. So that's in our second step of this life cycle. And in terms of our proof generation, all zkVMs have a prover component to generate proofs. It varies across zkVMs depending on the design choice for that proof system, as well as any hardware configurations that are involved. We'll go into some more details of that in a bit, specifically for zkMIPS. And in terms of verification, many zkVMs like ZKM use smart contracts to verify proofs on chain. Another value proposition for zkVMs is its breadth for different use cases for different applications in terms of our last step here in the life cycle. So for zkMIPS specifically, we're targeting the MIPS instruction set. So this can be applied to those both in blockchain and non-blockchain settings. For zkVMs focused more on privacy, use cases with private computations are now possible on public blockchains. But ZKM's main application is focused right now on interoperability, so providing unified native liquidity across different independent, incompatible ecosystems. Now, what zkVMs also do is remove all the trust assumptions that are present in our traditional forms of verifying that a computation was done correctly. Remember when we previously spoke about the status quo and how in our first outsourced trust model, there's always some trust assumptions involved. So for example, if you were to verify a computation using a standalone VM, or for example, like a cloud service provider, you would have to make a couple of assumptions in this process. So one is the configuration of the VM or the environment that you're using is correct. Another is that the program that encodes the computation is ran correctly and it's executed as intended. And then the biggest trust assumption is that the results of the computation that's given to you are correct. If we add the ZK component here, all of these trust assumptions that we're currently so accustomed to accepting to are all eliminated, and only ZK proofs that are generated can only be used for these valid computations. Now, why else would you use a zkVM? Our alternative here is to write a ZK circuit. A circuit is an encoding of a program into what are called constraints that prove the correct execution of a program. So there's an input and a program that's written in a specialized language for ZK applications. So for example, some ZK DSLs are like Circom, Noir, Leo, and both of these are fed into the circuit where, like the zkVM, a final state and an accompanying proof are outputted. In this case, if we look at a direct comparison, even though circuits are highly optimized and are generally efficient, because the circuit is going to be exactly what's needed for the program without you having to deal with any extra components like memory, it's still typically better to make that circuit constructed into an actual VM to use zkVMs in this scenario. So looking at the differences between a circuit and zkVM, with a zkVM, instead of a circuit being equivalent to a program, we can have a circuit that knows how to execute that program. And while a circuit is specific to each program and a special verifier needs to be defined each and every time, a zkVM can be thought of as a generalized universal circuit. So you only need to define the verifier once. And another benefit that we previously touched on that zkVMs have is an ease of adoption. Any developer can use a zkVM because they can use their preferred high-level languages that they're already familiar with, like C, Rust, Go, Solidity, since programs written in those languages will be compiled down to machine code regardless. But whereas to circuits, only specific developers can do this because you need the additional knowledge of writing in specialized ZK languages, writing circuits, and then also other background knowledge, defining constraints, some other requirements in cryptography. So there's a pretty steep learning curve involved, but in zkVMs, you don't need anything additional to learn before you can start implementing. Now, for this reason, a lot of zkVMs emphasize the benefit of how developers are able to use the time to build applications and not circuits. zkVMs also have a pretty easy path to recursion. So after running your first program, you can take the proof generated and pass it as an input, and then run a verification program and get another proof that proves that that first proof that you generated was correct. That recursion aspect is very difficult with circuits. Now, if we compare zkVMs to zkEVMs, one of the main benefits for zkVMs is that they are built on well-established and unchanging instruction sets like MIPS, whereas the EVM frequently undergoes minor opcode changes, and that may lead to the ZK circuit changing as well. In terms of stability, zkEVMs only support Ethereum Geth, but zkVMs can support programs written in many different languages, and these have applications in non-blockchain scenarios as well. And those are really the main value propositions for using zkVMs. Over here, this is a landscape map that was made by House of ZK. It's a media and podcast channel that was originally spun out by ZKM. But when we scope out a bit and examine the broader ZK landscape as a whole, we're seeing ZK projects become more and more specialized and optimized for specific stages of that proof lifecycle. So proving services, for example, as we see here, all these projects are working on building proving services. They're very focused on scalability and also scalability and reducing costs for those proof generation steps because that part can be very expensive. But with decentralization, some are also focused on providing a decentralized proving network. And also, for example, cross-chain projects here, a lot of them are focused on that interoperability aspect. Some of them are addressing the issue of fragmented liquidity. Layer ones include verification layers and provide toolkits to write ZK applications. So it's really focused on optimizing for that developer experience. You can also see some ZK-EVM solutions over here as well on this map. So that's just the specialized type of ZK-VM specifically for Ethereum. ZK-VM solutions, like what we see here, those vary in terms of ISA. So for example, we have some zkVMs here that are using the RISC-V instruction set. And these projects on the maps are a lot of the main ZK infrastructure projects that will help lay the ground for wider scale, real world ZK applications to be built on top of them. And most of us here have this shared vision of making ZK more widely adopted so that we're not limited to our conventional ways of trust and re-execution for our computations. In terms of broader use cases that ZK can enable, there are quite a lot of projects in the space working on those that are focused on like the privacy aspect of ZK, the verifiable compute aspect, and then also both. So for example, bridging for ZKM's universal L2, we can utilize any chains underlying layer 2 as an interoperability mechanism for cross-chain messaging. And it's also verified using ZK proofs without having to implement an actual bridge. ZK-TLS is another popular use case that we're seeing a lot of today, which involves validating Web 2 data securely from any website to the Web 3 ecosystem without having to disclose any personal information. ZK coprocessors were able to now access historical data on Ethereum, ZK email, that involves you're able to complete things like authentication, account recovery for your email using ZK. zkML, we see have applications in verifying results from ML models and seeing that they're not secretly manipulated. And then there are some projects that are also working on having private transactions on the blockchain. Now, going into the next part, let's look into MIPS and why we're using this specific instruction set architecture. So ZKM uses the MIPS 32 microarchitecture. All programs, no matter their language, will be compiled to machine code MIPS programs so that it's understandable to the VM. And looking at the specific benefits of MIPS, well, first, it has a stable design. There's no need to frequently redesign these ZKP circuits. And unlike EVM bytecode, which may undergo those frequent opcode changes like what we discussed earlier, or RISC-V, which has custom instructions, MIPS has a more streamlined set of opcodes for efficiency. And MIPS itself is has a very strong industry presence. It's pretty well established. It's been around for around 4 decades, so it has a very mature ecosystem compared to some of the other ISAs in the market. Now, on to our last part, we'll take a deeper look into zkMIPS specifically and how it works. So over here, this is a broad step-by-step overview on all of the components that are involved within zkMIPS. And this process can be separated into 3 main parts: the program execution, proof generation, and proof verification phases. In the first part of program execution, we take a program which is written in a higher level language. Right now, zkMIPS is compatible with Go and Rust, and that program is fed into the MIPS compiler, which compiles the program into a MIPS ELF binary. That's the executable format for MIPS. And this ELF file will be readable to the VM by converting the source code into machine code. So source code that's written by the developer into machine code, so it's readable to the VM. And that ELF loader will load the MIPS ELF binary file into the MIPS VM. The MIPS VM will execute the compiled program and generate an execution trace. The prover can use that execution trace to prove the program. And any high-level language can compile down to MIPS. we'll get a sequence of MIPS instructions as a result. So how this looks like is after each instruction is executed, which is shown on our left side table here, we'll get a value for each register that's based on the instruction. So for example, in row I, we can see that the data operation here is addition. So the instruction is saying add the value from register 5 to the value in register 6, put that result in register 7. Here, 13 plus 21 is 34. But after going through all of those instructions, we'll get the trace table, which is shown on the right side here. And remember that trace table is a representation of the execution trace that the prover will use. And so the prover here will take that generated execution trace and check that the program was executed correctly, and also generate a proof for that correct program execution. There are 4 main proof layers that are involved in this process: Stark, Logup, Plonk, and then also Groth16. We'll very briefly go into the functions for each one. First, the execution trace, which is shown on the left side, is split into individual segments, which is shown on the right side here. Segments are small sequential executions from the program. And with these segments, they're then divided further into modules, and those are even smaller executions from the segments. Splitting the program into segments and then into modules, the reason why we do that is because it helps with that succinctness aspect and lowers the overall computational expense. From here, the instructions of each segment are divided into 4 different modular tables. So we have the arithmetic, logic, memory, and control, depending on its operation. The operations here are arithmetic. The instructions will go into the arithmetic table. If it's a logic-based operation, it'll go into the logic table, and so on. And now we reach our first layer of this proving stack, which are Stark-based proofs. These modules are proven independently with a protocol called Fry using Stark proofs, and as a result, we'll have our arithmetic, memory, logic, and control proofs that are generated. In this next part, we use a lookup scheme called Logup, and that shows that the segment is contained in the modular table, and it's used to prove that the program instructions were correctly verified in their specific modules. All of those modular proofs, so the arithmetic, logic, control, memory proofs, are combined into one single proof for each segment. They're aggregated together. And in the next part, which involves Plonk, all of the segment proofs from the previous layer are recursively combined using continuation into a single proof. And this proof proves the correctness of the entire program trace. And in this last part, it's really optional for the proof generation process, but to enable for on-chain computation, the final continuation proof is turned into an EVM-friendly format using Groth16. And this allows for that final proof to be verified on the layer 1. And I just gave a brief overview of the prover, but if you want to learn some more details about the proving stack, be sure to check out the zkMIPS white paper, and then also this blog article about the architecture written by the R&D team. And so after we have the proof generation, that final proof is the zkMIPS proof that shows the correct execution of that program. Most of these techniques that we see here, the reason why we use them is to decrease the overall final proof size and also decrease the time it takes to prove it. In the final part of that zkMIPS process, which is external to proof generation, is proof verification. So once the final proof has been generated, the verifier verifies the results of the executed program using the proof. It will check the proof and accept or reject the result. So in our case, the verifier comes in the form of a smart contract. As an overview of this process, it's always starts with that end user's action. The end user wants to prove the correct execution of a program. And then the program that the end user creates run in zkMIPS's execution environment, and that will compile to MIPS so that it's readable to the VM. And then in the proof generation, a zkMIPS proof for the program's correct execution can be either outsourced to zkM's prover service or be generated locally. And once the zkMIPS proof is generated, a verifier contract will verify it. And in the case of proving the correctness of blockchain-based transactions, once the proof is verified on-chain, that transaction is considered to be settled. Looking at how this works in an example, so just wanted to mention, we also touched on this very briefly, but ZKM is building an entangled rollup network. So these layer 2s on the entangled rollup network can be used as interoperability mechanisms to facilitate cross-chain transfers without having to use the architecture of a bridge. So in this case, if we want to transfer 100 USDT between two different networks, for example, from Ethereum to Avalanche using this universal L2 system, first that 100 USDT is deposited onto the Ethereum L2, and then a proof that that 100 USDT was burned on the L2 will be generated off-chain. That proof will be verified by a verification contract on the destination chain, which in this case is Avalanche. And then that 100 USDT can then be minted and then withdrawn into the Avalanche layer 1. So that user will receive that 100 USDT on Avalanche. And this diagram was taken from ZKM's settlement.network page. If you want to see some more examples of use cases with entangled rollups, be sure to check that out. And that concludes our part 1 of this two-part series. In our next part, we'll be going into a demo with a Go program that proves that the user knows the value of a corresponding SHA-256 hash using ZKM's project template. So I'll see you then.